Particles A and B of mass 6 kg and 10 kg respectively are connected by a light, inextensible string over a smooth pulley as shown. So we've got a mass here of 6 kg, a mass here of 10 kilograms. The string is inextensible, it doesn't stretch or get smaller, and we've got a smooth pulley. A is on a rough table, so there'll be some sort of friction, and there's a frictional force of 12 newtons acting on it when B is released. Find the tension in the string and the acceleration of the system. Particle B takes 0.6 seconds to fall d meters to the ground. Find the value of d. When B hits the ground, A carries on moving along the table. How long does it take A to stop after B hits the ground? Okay, what is 100% essential when you do this type of problem is to draw a force diagram. You don't need to draw a posh one like that, but you need to draw a reasonable large diagram and then put on the forces. So for the 6 kilogram mass, there will be the weight acting downward, 6g newtons, and its reaction with the table. There'll be a frictional force of 12 newtons, which is F, and there'll be a tension in the string here. For the 10 kilogram mass, there'll be the tension in the string here, which will be the same as the tension of the tension here, and the weight acting downwards, which is 10g newtons. There will be an acceleration when the system's released, going in that direction. So resolving forces using Newton's second law, so using F is equal to ma. So for the 6 kilogram mass, we've got T going in this direction, minus 12 is going to equal to ma, which is going to be the mass, which is 6 times A, which I don't know. And then for the 10 kilogram mass, we've got 10g newtons minus T is going to be equal to 10 times the acceleration. Right, so we've got two equations here, so we'll label them 1 and 2, and we'll now solve those simultaneously. It's quite easy to do. You just need to do 1 plus 2, and then that eliminates t, because you've got t plus minus t, they disappear. So you're going to get 10g minus 12 is equal to 16a. And therefore you can find a by doing 10g minus 12 divided by 16. Using g as 9.8 meters per second squared, then A will be 5.375 meters per second squared. Right, we now need to substitute that into equation 1 or 2. We'll do 1. So we're going to have that T minus 12 is going to be 6 times A, which is 5.375. Don't use one that's been rounded off. And that's going to give that T is 6 times 5.375 plus 12, which gives 44.25 newtons. Right, the particle then B will then fall. It takes 0.6 seconds to fall. The initial velocity when it's released will be 0, so U will be equal to 0. So substituting my value of A into here, we're going to get that 0 times the time, which is 0.6, plus a half, times 5.375 times the time, which is 0.6 squared. The 0.6 came from the question. That gives me 0.967 meters, and that this one we can round off because we're not going to use it again to be 0.968 meters to 3 significant figures. So when B hits the ground, the tension will go out of the string, but A will continue to move along the rough table. So when B hits the ground, the tension will go out of the string. The speed of A as B hits the ground, and we're going to have a new acceleration here. We're going to take this direction as positive. We will have a new acceleration. Will be, if we use V is equal to U plus AT, but as it actually hits the ground, the acceleration will be 5.375, just as it hits, because these two will have the same acceleration at that particular time. That's going to give that the initial velocity of this as B hits the ground being 3.225 meters per second. Now, because this has hit the ground, the acceleration is now going to change. So we need to now calculate a new acceleration. So the new acceleration, so there's no tension acting on this, will be 12, but this is acting in the opposite direction. So it'll be using F is equal to ma. Minus 12 will be equal to 6 times a, which will give that a will be equal to minus 0.5 meters per second squared. So it's acting in the opposite direction, so it will start to slow particle A down. Right, calculating the time rearranging this one will be v minus u over a, but we need to remember this. The final velocity of this thing, because we want to know where it stopped, will be 0 because a will have stopped, and the initial velocity will be 3.225. So things get swapped around a little bit. So substituting that in, we're going to get that t is 0 minus 3.225 divided by minus 0.5, which will give a time of 6.45 seconds. So this is actually going to continue along quite a long time compared with this one hitting the ground. Okay, so this has been a video to show you how to calculate the tension and acceleration of a connected object. Being able to calculate a distance that a particular one of the particles falls, and then calculating the time for one of the other particle to stop. I hope you've understood, and I thank you very much for watching.